This lesson will be a brief introduction to the theory of sets. So we'll start here with some examples of sets, and we'll talk a little bit about the notation, how we write sets. Then we'll work through some exercises. So first of all, a set is a collection of objects. For the purposes of our class, we're often going to be using collections of numbers, but they don't have to be. A collection of objects is a set, and we express them in writing by using the second bracket, as you see here, and then listing the elements separated by commas. So here are some common examples of sets and their accompanying symbols. The natural numbers is the group of numbers which are sometimes called counting numbers. And as you can see here, they are 0, 1, 2, 3, and so on. We can just put ... when it's clear what the rule is that we're using. And we'll use this script capital N to indicate the natural numbers for the rest of the course. Now, I just want to point out here that depending on which math book you're reading, some people will include 0 in the set of natural numbers and some will not. So it's important to remember we'll be including 0 for the rest of this course. Another set of numbers that we'll be using a lot is the integers, which we denote with script Z. So anytime you see script Z, you'll understand we're talking about the integers. And what are the integers? Well, we have all of the natural numbers, 0, 1, 2, 3, and so on, but we also include -1, -2, -3. Then we have the rational numbers. We use script Q to denote the rational numbers, and these are numbers that can be expressed as a ratio or a fraction of integers. The real numbers and the complex numbers. For the real numbers, we use script R, and for the complex numbers, script C. So you'll want to familiarize yourself with that notation because we'll be using that throughout the course. So as we've seen here, we can express a set by just listing the elements. And even if the set is very large, once the pattern becomes clear, we can write ... One other way of expressing a set is called set builder notation. So here's an example. For the rational numbers, you could describe the set this way. And the way we would read this is the set of rational numbers is equal to the set of all A over B, such that A and B are integers and B is not 0. So if you look at this set builder notation, first you're going to have something. In our case, it's the set of all A over B. And then this straight line means such that. Then the properties that your A over B have to satisfy are here to the right. In this case, we had two properties. First, A and B are both integers, and second, B is not 0. So this is called set builder notation, and in a little while we'll get some practice using it. One thing to keep in mind is that there is not a unique way to express many sets. Many sets could be expressed in many ways. And we'll also see some examples of that coming up. Here we have a definition. A set is finite if it has a finite number of elements. If it's not finite, then we'll call it an infinite set. The number of elements in the set will be the cardinality of the set. So if you're asked to find the cardinality of a set, you can count the number of elements if it's a finite set. And then there's another note here that there are different infinite cardinalities, and we don't really have the tools yet to discuss the distinction between these different infinite cardinalities. So for now, we'll just mostly talk about finite sets. When we have two sets, or when we have a set, an important concept to understand is that of a subset. So your definition here says let A and B be sets. We say that A is a subset of B if and only if every element of A is an element of B. So we start with the set B, another set A, And if everything in A is also in B, then we get to say A is a subset of B. So there are some examples here. If A is the set 3, 5, and 8, and B is the set 5, 8, 3, 2, and 6, then A is inside B because 3, 5, and 8 are inside B. Another very important example is here we can note that the natural numbers, the counting numbers 0, 1, 2, 3, and so on, are a subset of the integers, because the integers include the counting numbers, but we also get all of the negative counting numbers. And the integers are a subset of the rationals because any integer could be expressed as the integer over 1, therefore making it rational. All of the rational numbers are real numbers, and all of the real numbers are complex numbers. If, for example, you had a set here like S is equal to 3, 5, and 8, T is equal to 5, 3, and 8, then not only is S inside of T, but T is also inside of S. So this illustrates that it doesn't matter which order we write these numbers in a set. You're just collecting the objects. So if you collect the objects in one order or another, it's the same collection of objects. Another common practice for sets is that if we have the same number twice, we generally only write it once. For the purpose of our class, if an element is in a set twice, you only have to write it once. We already know that it's in the set. So that last example of S and T demonstrates the next definition, which is set equality. So two sets are equal if every element of a set A is inside B and every element of a set B is inside A. So another notion of saying that two sets are equal is saying that A is a subset of B and B is a subset of A, just like we had in example 3 with S and T. So then they are the same set. All right. We want to stop and point out here that we use the phrase if and only if in this lecture. And in mathematics, and for the purpose of our class, whenever we see if and only if, that's the same thing as just saying that two sentences or two expressions are equivalent. The concept being defined can be replaced by the other one. One last very important set that we need to talk about is the empty set. So occasionally we'll have a reason to use an empty set, and we use the Greek letter C to represent the empty set. You could also start your second bracket and then close your second bracket. And as you can see, there's nothing listed inside the set. The set has no elements, so it's empty. We denote that as phi, the empty set, or the null set. Now, from our above definition of a subset, we can clearly see that any set A is a subset of itself, and the empty set is a subset of any set A, because they're both satisfying the requirements. A is a subset of itself because all of the elements of A are in A, and the empty set is a subset of A because all of the elements in the empty set, there are none, they are in A. So we call A an improper subset of itself, but any other subset of A, including the empty set, we'll call a proper subset. All right, so let's do some examples here to make these ideas a little bit more concrete. So exercise 1 asks us to list 4 elements of each of the following sets. And these sets appear to be written in set builder notation, so we'll first have to make sure that we understand what the set is saying. So for A, we have this symbol means belongs to. And we'll also be using that throughout the course. So the way we would read this is k belongs to the set of natural numbers. And remember, this straight bar is such that k minus 1 is a multiple of 7. So the set, the way it's described, is all of the natural numbers, so that if you subtract 1, you get a multiple of 7. So what are some examples of that? Well, I would say 8 should be in this set because 8 minus 1 is 7, and 7 is certainly a multiple of 7. Or you could have 15 because 15 minus 1 is 14, and that's clearly a multiple of 7. Also, the number 1, since 1 minus 1 is 0, and 0 is a multiple of 7, and maybe 71. 71 minus 1 is 70, which is a multiple of 7. We were asked to list 4 elements, so I'm going to stop here, but there are many, many more. We could keep going. Now, I mentioned before that sets don't have to be collections of numbers. So here's an example. B says, the set of all x such that x is a fruit and its skin is normally eaten. Well, this is sort of a matter of preference, but typically we don't eat a banana peel and we don't eat an orange peel. So those would not belong to the set, but maybe something like apple. Some people don't eat the skin, but you can. Most people do, I'd say. Peach, pear, maybe grape. And again, there are many more examples. And you can also think about, as I mentioned, things that are not in the set, like an orange. Okay. C. C is the set of all x in the set of rational numbers such that 1 over x is an integer. So what does it mean x is a rational number? Let's remind ourselves. X is a rational number. That means x is of the form a over b, where a and b are integers and b is not 0. Then in order for 1 over a over b to belong to z, we must have that b over a is an integer. So in fact, we'd be looking for things that are of the form one over a number, an integer. So we want a is equal to 1. That's what I'm trying to say. Okay, so if a equals 1, and we already knew b was an integer, then b over a is an integer, and we're in the set. So what are some examples of that? Well, we could have x equals 1/2. Then 1 over x equals 2. And that's an integer. Or we could have x equals 1/4, then 1 over x equals 4, and that's an integer. So if I wanted to list 4 elements from this set, I might pick 1 over 2, maybe 1 over 4, 1 over 19, negative 1 over 19. And there are many more. The next set, D, to n, such that n is an integer and n is less than 0. So we're starting with integers less than 0, but the elements of our set are actually going to be 2 times the integer. So if n is, I'm looking for an integer less than 0, so maybe negative 1, then 2n is negative 2. So the elements in this set are going to be like negative 2, or maybe negative 4, which is 2 times the integer negative 2. Or we could have negative 38, which is 2 times the integer negative 19. Or maybe negative 1000, which is 2 times the integer negative 500. So in each case, we've got 2 times an integer that's strictly less than 0. And the last example here, s such that s is equal to 1 plus 2 plus ... plus n, or some natural number n. So s could be 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. So we're adding the natural numbers in order, and it's just a matter of where we stop. So we could have 1 plus 2 plus 3, which is 6, 1 plus 2 plus 3 plus 4, which is 10, 1 plus 2 plus 3 plus 4 plus 5, which is 15, and so on. Or we could take something like 55, which should be the sum of the first 10 positive natural numbers. So that's the first exercise. Another exercise asks us to list all of the elements of the following sets. So let's look at A. Again, our sets appear to be written in set builder notation. The first set is 1 over n, such that n belongs to the set 3, 4, 5, and 6. So this is interesting because it shows us that when we're using set builder notation and we're listing these properties that our n needs to satisfy, we can put another set there. It doesn't just have to be that n is a natural number or an integer. We can do whatever we want. So let's say 1 over n such that n belongs to 3, 4, 5, and 6, and we're supposed to list all of the elements. So all of the elements would be 1/3, 1/4, 1/5, and 1/6. And there are no other elements in this set. For B, alpha belongs to the alphabet such that alpha precedes F. So if we think about the alphabet as being a set, what would it be? It would be the set A, comma B, comma C, comma D, comma E, comma F. Keep going until we get X, Y, and Z. That would be our alphabet. So all of the elements which precede F should just be A, B, C, D, and E. So the set described here in part B is a subset of the alphabet that just contains the first 5 letters. For part C, we have n squared such that n is equal to -2, -1, 0, 1, or 2. So if I wanted to start listing the elements, I would say -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So I could write this set as the set 0, 1, and 4, or I could write it as the set 4, 1, 0, 1, and 4. As we mentioned, we'll typically only write each element once. Once I've counted it in my set, I don't need to put it in there again. So more commonly you would see this should be the set 0, 1, and 4. Or if we're asked to list the elements only, the elements would be 0, 1, and 4. In the next exercise, we're asked to describe the sets in set builder notation. So now our sets are not in set builder notation. We want to write the set builder notation. And as we discussed, for any given set, there are probably many different ways to express it. So I'll just show you some examples. The first set is 5, 7, 9, ... comma 77 and 79. Because of the dot dot dots, I know that all the numbers in between should be following a pattern. So what it looks like to me is these are all of the odd numbers between 5 and 79. So one way of saying that is x such that x is odd and 5 is less than or equal to x is less than or equal to 79. If we wrote that, we would have clearly described the set, and anyone who was asked could write down the set again. They could say it's going to be 5, 7, 9, dot, 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 77 and 79. But if we wanted to get creative, we could come up with plenty of ways to describe this set. What about n plus 4 such that n is odd, n is a natural number, and n is less than or equal to 75. Would that not be the same set? Because if I take any natural number which is odd, that starts at 1, and if I add 4, I get 5. Then 3, I add 4 and I get 7. Then 5, I add 4 and I get 9. So it seems like I can get the exact same set using either of these definitions. So let's look at B, the rational numbers that are strictly between -1 and 1. Probably the most straightforward way to describe this set is just to say x is a rational number such that -1 is less than x is less than 1, and close the bracket. The word here was strictly between -1 and 1, and so that's why I've chosen to use less than instead of less than equal to. The next set that we're asked to write in set builder notation is the even integers. So I could say x is an integer such that x is even. That would be fine, that's clear enough. Or I could write x such that x is an integer and x is even. Or maybe I could write x is an integer such that x is equal to 2 times k, and k is an integer. In any of these formats, I'm going to recapture all of the information that I wanted. I'm going to get every even integer. The last one, the set D, is -18, -9, 0, 9, 18, 27, and so on. So what this looks like to me is all of the multiples of 9, starting at -18, and then going on forever. So I'd probably say this is the set of all k, such that k is a multiple of 9. And k is greater than or equal to -18. If I had the dot dot dots going on both sides, like if I had dot 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 here, then I would say it's all of the multiples of 9. But since I started at -18, I had to make that known when I wrote my set builder notation. And you can also see that I've used n some places, I've used x, I've used k. So that's basically doesn't really matter. Oftentimes you'll see n used in conjunction with the natural numbers, and maybe k used in conjunction with the integers, and x with the real numbers. But it really doesn't matter as long as it's clearly defined that your letter is an integer or a natural number. Use whatever letter you like. All right. Here's another example where we're asked to use the set builder notation to describe the sets. So I have the set 1, 2, 3, 4, 5, 6, 7. The most straightforward way to describe it, I'd say, is probably x in the set of natural numbers such that 1 is less equal to x is less equal to 7. Or I could have said x in the set of natural numbers such that 0 less than x less than 8. For B, I have 1, 10, 100, 1,000, 10,000. So I'd probably say this is the set of 10 to the power n, such that n is a natural number, and n is less than or equal to 5, less than or equal to 4. But again, there's probably many ways to describe it. 1, 1/2, 1/3, 1/4, 1/5, dot, dot, dot. I'm going to say that that's 1 over n, such that n is a natural number, and n is not 0, because in our class we're assuming that 0 is a natural number, so it's very important that we make that distinction. D is just the set that contains 0. We call this a singleton if it has only one element. And if you wanted to use set builder notation to describe it, you could probably say x such that x equals 0. Okay, let's look at one last example here. We're given 3 sets, A, B, and C. A is the set 0, 2, and 3. B is the set 2 and 3. C is the set 1, 5, and 9. And we want to determine if the following statements are true, and then give reasons for why they are true or not true. So first of all, 3 belongs to A. 3 belongs to A is true, and that's because 3 belongs to A. As simple as that. B, singleton 3 belongs to A. Is that true? That's not true. So there's a difference here between just the number 3, or what we have here is the set 3. The set 3 is not an element of A. Only the number 3 is an element of A. So I would say false, because the set 3 is not in A. Then the third one is the set 3 a subset of A? This is absolutely true. This is the same as saying that 3 is in A. Because 3 is in A, the set 3 is a subset of A. So it's important to make this distinction between B and C. The set 3 is a subset of A. It is not in A or an element of A. All right. What about D? Is B a subset of A? So the set 2 and 3, is it a subset of the set 0, 2, and 3? It is. And that's because 2 is in A and 3 is in A. So the set 2, 3 is in the set 0, 2, 3. What about, is A a subset of B? Well, it's not, because A has more elements than B. There's an element of A which isn't in B. The number 0 is in A. It's not in B. So A is not a subset of B. Is the empty set a subset of C? C is the set 1, 5, and 9, but that doesn't really matter because we already said that the empty set, we're going to say that it's a subset of all sets. And that's because all of the elements in the empty set, and of course there aren't any, so this is sort of true by default, all elements in the empty set are in C. What about, does the empty set belong to A? A is the set 0, 2, and 3. So the empty set does not belong to A. So again, the difference here between belonging to a set and being a subset of a set. Very important distinction to make. And then last question, true or false, A is a subset of A. And again, we said that that's always going to be true. We're going to let a set be a subset of itself because all the elements in A are in A. And that's what we have to check to call something a subset. Are all of the elements in one set inside the other? If so, it's a subset. But we want to note here that A is not a proper subset of itself. But it is a subset. So the last thing we have is the definition of the set is a little bit vague. And there's something called Russell's paradox. And for this reason, we have to leave this a little bit vague. Many mathematics and logic books contain reference to this paradox, or will explain this paradox to you, and your instructor has provided some possible references for you. Your instructor would like you to find one such reference and read about this paradox. It's fascinating, and it will shed a little bit of light onto set theory for you.